This is chapter 6 for the Chang 10th edition on thermochemistry. To begin with, it talks about different types of energy, which first off, to define energy is the capacity to do work. There's radiant energy, typically from the sun. Thermal energy, motion of molecules creating that heat. Chemical energy is the energy stored within chemical bonds. Potential energy is the available energy. And then one other thing mentioned is the law of conservation of energy, which is the total energy in the universe is constant. That idea that energy cannot be created or destroyed, just transferred from one form to another. You've often referred to that as the first law of thermodynamics. More terms to mention within this unit is first off heat. Heat is referred to as the transfer of thermal energy between two bodies at different temperatures. The system is what we are focusing on when we talk about thermodynamics. The surroundings is everything outside of the system. So there's one point of view, and then there's everything else around it. As for different types of systems, we can have an open system, which allows for the transfer of mass and energy. We could have a closed system, which allows for the transfer of just energy. Or we could have an isolated system that does not allow a transfer of energy or mass. Endothermic process is when heat is being supplied to the system from the surroundings. And then an exothermic is the system gives off heat to the surroundings. One of the things we're going to be going over in a little bit is a value called delta H to represent what we refer to as enthalpy. And in an endothermic system, when you take in heat from the outside, that's a positive delta H. Exothermic is the system giving off to the surroundings, that is a negative delta H. Thermodynamics is stated as the scientific study of interconversions of heat and other kinds of energy. Now, one of the things that's mentioned is a state function within there, that properties that are determined by the state of the system regardless of how that condition was achieved. A few equations to get into then, starting off with delta equals Q plus W. The Q stands for heat, W is the work, and now will equal the total change in energy of a system. Positive values means the surroundings once again onto the systems. An expanding gas does 279 joules of work on the surroundings while absorbing 216 joules of heat. What is the change in energy is the first equation that we'll do up here on the board. So it gives you both a work value and a heat value to solve for the delta E. So once again, delta E is Q plus W. The only thing you have to keep in mind is the positive and negative sign. So once again, system onto the surroundings is going to be a negative value. Surroundings onto the system is a positive value. So a gas does 279 joules of work on the surroundings means that's a negative 279 joules because it is doing work onto the surroundings or giving off work. At the same time, the question says it's absorbing 216 joules of energy. So this is 216 joules. So 216 joules minus 279 joules means the total change in energy is a negative 63 joules. So in other words, the system is losing 63 joules of energy overall. The second equation we have to be aware of is what work equals. When we talk about this expanding part, work equals negative P times delta V. And there's one conversion that we need to know within there, because work is typically measured in a joule value. Notice the joules that I have on the board here. But when we take pressure, which is atmospheres, times volume, which is in liters, we don't get joules. So there's a conversion between the two, and that's what this last question here is going to go over. Say a gas expands from 264 milliliters to 971 milliliters at a constant temperature. Calculate the work done against a pressure of 4 atmospheres. So the equation we're using is the work equals negative P delta V. So first off, we're going to solve for the work. The pressure given to us is going to be 4 atmospheres. And again, I'm just putting the negative sign right away there. Delta V. Delta V has to be in liters, so first off I convert my 264 milliliters into 0.264 liters and my 971 milliliters into 0.971. But to figure out the change in volume or a delta of anything is always final minus initial. So 971 minus 264, convert that into liters, would get me 0.707 liters, or 707 milliliters. When I first multiply these two values, I end up getting 2.828. And again, it's a negative value, atmosphere liter. The problem is this is not a unit of work. So now I have to use that conversion I just said before of 101.3 joules per 1 liter atmosphere. If I do that, I will get my final answer in a more acceptable unit. I'll end up having 286 joules. And again, that is a negative value to begin with, which just refers to the fact of the system giving to the surroundings. As I mentioned before, there's another term within thermodynamics you have to be aware of, referred to as enthalpy. Enthalpy is the quantity used to describe heat change. There's several equations dealing with it. This is an equation that we did not use very much in class of delta H, the change in enthalpy equaling the change in energy plus pressure times delta V. Another one that we did use a lot more is the enthalpy of the products minus the enthalpy of the reactants. Delta H values refer to all the reacting species in their molar quantities, the last thing to mention. And here is the question that we'll work on next. It says calculate the heat, it should say heat, not head, heat involved when 266 grams of P4 burns in air to make tetraphosphorus decaoxide with a delta H of negative 3,013 kilojoules per mole. So the first thing I'm going to do is write the balanced equation on the board for that. Here's P4 plus 5O2 is going to make my tetraphosphorus P4 decaoxide, P4O10. Now that I have that balanced equation, I can write down what I started off with. 266 grams of P4. The end of question gives you negative 3,013 kilojoules per mole. So there's only 1 mole of P4 in this problem because that's the coefficient in front of it, just like there's 5 moles of O2 in this question. But I need to figure out how many moles I have first. So what I'm going to do is convert this into moles. 1 mole, look for the mass of P4 on the periodic table, so phosphorus times 4, is 123.88 grams. Now that I have that value, that will give me my number of moles, which is 2.15 moles. Now that I have that, I can multiply by the 3,013 kilojoules per mole. Again, it is technically a negative value within this question. So now my moles will cancel out. I'll be left with how many kilojoules of energy that many grams of P4 could give me. And my answer, the negative value just refers to it giving off energy, is negative 6,470 kilojoules. So once again, for this particular problem, the equation was given a delta H. So in this particular equation, 1 mole would be that negative 3013, or 5 moles of O2 would be that negative 3013, or 1 mole of P4O10 would be that negative 3013. So what I want to do is figure out how many moles I had. So I convert my grams into moles, and then I just multiply out. My units cancel, leave me as kilojoules. Something that's commonly done within thermochemistry is something called calorimetry. This is to measure the heat change that occurs in different processes. There's several equations associated with this, and this is one thing that our textbook might do different than the AP textbook, where they give a capital C, and that is referring to the heat capacity, equals the mass times the specific heat. You may see on the AP test having a lowercase c for the heat capacity, or a specific heat capacity they refer to it as. So just be careful of that. I would almost guarantee that you need to memorize the specific heat of water. So the S value that we use in class, or again C value, of 4.184 joules per gram degree Celsius. Our book then gave us this equation, Q, which is standing for heat, equals ms delta T, where m is the mass of the substance, S is the specific heat, but once again, you might see MC delta T, and delta T is going to be the change in temperature. Here's a question that we can answer. It says an 869 gram iron bar cools from 94 degrees Celsius to 5 degrees Celsius with an S value of 0.444. How much heat is released in kilojoules? So if we do this one on the board, I would start off with Q equals ms delta T. My mass in this question is 869, and that's grams. The S value is 0.444. That's joules per gram degree Celsius. Delta T, once again, you would take final minus initial. So originally, this is going to give me negative 89 degrees Celsius, because 5 minus 94 would give me that. That gives me a Q value of negative 34,000 joules. Which once again, in thermodynamics, a negative value means it's giving off. A hot bar of iron is giving off heat, so it's a negative value. The question does not ask for the answer in joules, though it asks for in kilojoules, which most of you can probably convert from kilojoules to joules very easily without doing a conversion. The conversion would be 1 kilojoule for every 1,000 joules. That gives me 34 kilojoules is my final answer for that question. That would be a very simple calorimeter problem. What we're going to do is go over a couple more calorimeter problems that would be a little more difficult. There are two types of calorimeters. There are constant volume calorimeters, which is what we used in class, or there's what's referred to as bomb calorimeters. Bomb calorimeter will have its own heat capacity, which means you must add that to the water's m times s to get this Q overall. So another equation that our book gives us is Q equals capital C times delta T, where that capital C is the heat capacity of the calorimeter, and we might have to add waters to that as well. Here is a very long question for us to look at. It says 1.922 grams of methanol is burned in a bond calorimeter, raising the temperature of 1,000 milliliters of water by 4.20 degrees Celsius. The heat capacity of the calorimeter is 6.216. What is the molar heat of combustion of methanol? There's a lot we have to do within this question. The first thing we need to do is figure out the Q value of the calorimeter. The Q of just the calorimeter is going to be the big C delta T part. So if I plug that in, 6.216 is the C value given to us. The delta T is going to be 4.20. This will give us the Q for that part, which I end up getting, especially since it's kilojoules per degree Celsius for this unit here, 26.1 kilojoules. The next thing I need to do is when it says molar anything, molar heat of combustion, molar anything, is convert my 1.922 grams of methanol, convert that into moles of methanol, which methanol's formula is CH4O. You might see it as CH3OH otherwise. Mole conversion is 1 mole over 32.05 grams. And that will get me 0.5997 moles. Now I know my kilojoules, I know my moles. If I want to find molar heat of combustion, I'm going to divide the two. 26.1 kilojoules divided by 0.05997 moles. And that will give me my final answer of 435 kilojoules per mole. Sometimes you might have to also figure out the change for the water as well. In this particular problem, the calorimeter took care of that as well, so we didn't have to worry about that. What we did was more of the next slide on calorimeters of constant pressure, which is our styrofoam cups. So I misspoke before when I said the constant volume of styrofoam cups. We don't have to worry about the heat capacity of the calorimeter. So here's a more common problem we might have, is if 30.14 grams of stainless steel ball at 117.82 degrees Celsius is placed in a styrofoam cup with 120 milliliters of water at 18.44 degrees Celsius, what is the specific heat of the heat? Specific heat of all of it if the final temperature is 21.19. And I believe I should say the specific heat of the ball on there. What we need to do is figure out the S value, the specific heat of the ball. But we don't know that. We can solve for the Q value of water though, and using the first law of thermodynamics, if one thing gained heat, the other thing lost heat. So what I'm going to start off do is solving for the Q of the water, which is going to be ms delta T. The mass of the water is going to be 120. Because once again, water has a density of 1, so its milliliters are the same as its mass. The S value of water is 4.184. And finally, the temperature that the water had changed is going to end up being 2.75. The reason why it's 2.75 degrees Celsius is 18.44 is the start, 21.19 is the end, subtract the 2. This is going to give me the amount of heat the water gained, which is 1,380 joules. If this is the amount of heat the water gained, the stainless steel ball lost the same amount. So now I'm going to have the Q of the steel equaling ms delta T. My Q of steel is negative 1,380 joules. Again, it lost the heat that the water gained. The mass of the steel is 30.14. The S value is what I'm solving for, and the change in temperature is negative 96.63. Solve for S, I get 0.474, and that's going to be joules per gram degree Celsius. This is the more typical calorimeter problem that we went over in class. But again, keeping that idea of first law of thermodynamics of the Q of one thing, Q of the other. Standard enthalpy of reaction. There's two ways to solve for the standard enthalpy. There's the direct method, which would be the delta H of the reaction is the summation of the moles times the delta HF, the heat of formation for the products, minus that of the reactants. There's the indirect method as well, that's called Hess's law. When reactants are converted to products, the change in enthalpy is the same, whether the reaction takes place in one step or a series of steps. So it's referred to as a state function, because it doesn't matter how you get there, it just matters the start and the finish, really. So what we're going to do is a practice problem for each, starting with the direct method. Here's a question from the direct method. It says benzene combusts to produce carbon dioxide in liquid water. Find the heat, which is the kilojoules per gram, of benzene given the following standard enthalpy of formation values. So I give you the delta HF of all these different things. Once again, we need a balanced equation, because within that first enthalpy equation was the moles part of it. So if I write a balanced equation on the board for this, I have 2 of the C6H6 plus 15O2 is going to yield 12 CO2 plus 6 H2O. So now, if I want to find the delta H of the reaction, it's going to be products minus reactants. So to begin with, I'm going to take 12 times the delta H value for carbon dioxide, which is negative 393.5. And again, that's in kilojoules per mole. I'm going to add to that 6 times its value. Water's value is negative 285.8. These would be the products. Now I'm running out of room because I could just continue going on. I'm just going to subtract from it the reactants. 2 times the benzene value. The benzene value here would be 49.04. And I could look for the oxygen value. 15 times 0 isn't going to give me anything really. So all of this added up minus this will tell me the delta H of the reaction, which in this case is negative 6,535 kilojoules per mole. Once again, do not be alarmed about a negative delta H value. That simply means that the system is giving energy off to the surroundings, which in a combustion reaction, you want heat to be given off from the system to the surroundings. That's how things get heated up. So this would be the direct method. The last calculation we have is the indirect method. So if you read that question, it says find the standard enthalpy of formation given carbon disulfide from its elements, and here's the following equations. So sometimes we know equations and their delta H values. So maybe we can't look up the carbon's delta H of its graphite or the S of its rhombic value. But what we can do is take a series of equations and add them together to make this work out. First thing I need to do is figure out the equation of carbon disulfide forming from its elements. So that equation would be carbon plus 2 sulfur makes CS2. This is the equation I want to get to. On the smartboard is the equations that I have to begin with. So what I need to do is match these up somehow. You'll notice I have 1 carbon on my reactant side. Over here, I have one carbon on my reactant side. That equation is great the way it is. Carbon plus oxygen makes CO2. And that has a delta H value of negative 393.5. I have two sulfurs on my reactant side. Here I only have one sulfur on my reactant side. So I have to multiply everything in this equation by 2. So now I have 2 sulfurs plus 2 oxygens makes 2 SO2s. Since I multiplied everything here by 2, I have to multiply my delta H by 2. So negative 296.4 times 2 would get me that new value, which is negative 592.8. Lastly, I have CS2 on the product side here. I have CS2 on the reactant side here. So what I have to do is multiply by negative 1, or the inverse of that equation. So if I flip that equation around, it's CO2 plus 2SO2 yields CS2 plus 3O2. The delta H for that was originally negative 1073.6, but I need to multiply by negative 1. The reason why I'm multiplying by negative 1 is I'm showing the reverse reaction. Over here it's showing this as a reactant creating this, giving off energy. The reverse reaction that I have shown would do the exact opposite. So in other words, it's just going to be 1073. If I add these three values up, it will tell me the delta H of the reaction, which in this case would be 87.3 kilojoules per mole. Now, if you need convincing of this method working, I have 1, 2, 3 oxygens on my reactant side. I have 3 oxygens on my product side. They cancel each other out. I have 1 carbon dioxide in the product, 1 carbon dioxide in the reactant. They cancel each other out because they're on both sides. 2 SO2s, 2 SO2s. If I add up what's left, I have carbon plus 2 sulfurs making CS2, which is exactly what I wanted to get to. So once again, what you're doing in a Hess's law, which is an indirect method, is you're manipulating the equations given to you to make them look like the equation you want to get to. So if I had to multiply the second equation by 2, I had to multiply the delta H value by 2 as well. If I had to do the inverse of this equation to get the CS2 on the product side, I had to multiply this by the inverse, or negative 1 in that case. The very last thing, which there might not be much on at all, is the heat of solution. And you probably don't need to know this calculation of the delta H solution is U times the delta H of hydration. But U is referred to as the lattice energy. And this is a term you might need to be familiar with. Lattice energy is referred to the energy required to separate 1 mole of solid ionic compound into what's referred to as gaseous ions. They're free floating about. The heat of hydration is the enthalpy change associated with hydration, which once again is the taking in of water molecules by the ions. Last thing to mention here is the heat of dilution is the heat change associated with dilution, which we talked about this, that you never add water to a concentrated acid because it's highly exothermic. The solution can boil over and then cause harm to you. And that's the do as you order, add acid to water saying. This is the end of the first thermodynamics. We'll continue with this